this video, we are discussing design of branching airway. The airways of lung form a branching tree-like system that conducts air from trachea to alveoli. This branching airway tree represents the basic structural framework of lung. Space-filling nature of airway tree. The airway tree is a space-filling structure with its terminal branches distributed throughout the lung volume. The final arrangement of these branches is determined by the shape and size of thoracic cavity. The branching pattern of airway tree. Airway branching occurs by a dichotomous pattern in which each parent airway divides into two daughter branches. This process is repeated across successive generations. Number of airway generations. In human lung, the airway branching proceeds through a range of about 23 generations, with a range from approximately 18 to 30. This variability reflects differences in how the airway tree fills above the lung space. Changes in airway length and diameter. As the branching progresses, airway segments increase in length to span the available space, while airway diameter progressively decreases with each generation to ensure uniform filling of the lung. Diameter and supplied lung volume. The diameter of airway reflects the volume of peripheral lung tissue it supplies. Larger airways serve larger lung region, whereas smaller airways supply smaller peripheral units. Asymmetry of airway branching. Although the airway tree appears regular, branching is not perfectly symmetric. Daughter branches often differ in length and diameter, and this asymmetry is more pronounced in animal lungs than in humans. Law governing airway diameters. The progression of airway diameters follows optimization principles that relate the diameter of parent airway to the diameter of its daughter branches. Diameter reduction in symmetric dichotomous branching. In symmetric dichotomous airway tree, both daughter branches have equal diameter. Under this assumption, Hess-Murray law states that cube of parent airway diameter equal to sum of cubes of daughter airway diameters. This simplifies to a constant diameter reduction where each daughter airway has a diameter equal to parent diameter multiplied by 2 raised to the power of minus 1 by 3. Numerically, this represents a reduction factor of approximately 0.79 per generation. Using this relationship, the average airway diameter at any generation Z is given by the parent diameter multiplied by 2 raised to the power of minus Z by 3. Validity of diameter law in human airways. In human lung, the diameter relationship holds reasonably well for first 14 generations of conducting airways, with deviations occurring in more distal airways. Safety factor in small airways. In small airways, the diameter reduction factor is closer to 0.83 rather than theoretical optimum of 0.79. This provides a safety factor that improves physiological robustness. Clinical significance of diameter loss. The clinical significance of this diameter loss lies in the strong dependence of airflow resistance on airway radius. Small reduction in airway diameter can cause large increase in resistance. The relatively wider small airways provide a safety margin, explaining why disease affecting small airways can produce disproportionate airflow limitation. Conducting and acinar airways. The airway tree can be divided into conducting airways extending through approximately first 14 generation and acinar airways beyond this point, which are associated with alveolar structures. Transitional bronchioles. Transitional bronchioles mark the entry into acinus and represents a structural transition where alveoli first appear in airway wall. Distribution of airway resistance. Airway resistance is highest in medium-sized conducting bronchi and decreases rapidly towards lung periphery due to increase in total cross-sectional area. Fractal design and robustness of airway tree. As airway branching progresses, total cross-sectional area of airway tree increases, leading to progressive fall in airflow velocity towards periphery. Airway tree exhibits a self-similar branching pattern characteristic of fractal geometry with a fractal dimension close to 3, allowing efficient space filling. Although airway dimensions approach mathematical optimization, the final structure is modified to favor biological robustness rather than strict optimality. In summary, branching airway tree is a dichotomous space-filling structure governed by predictable diameter relationship described by Hess-Murray law, with adaptive modifications that enhance clinical and physiological robustness. First diagram shows fractal structure of airway tree. This image illustrates fractal space-filling design of branching airway tree. The same branching pattern is repeated at multiple scales, allowing the airways to distribute uniformly throughout the lung volume. A fractal dimension close to 3 explains how airway tree efficiently fills three-dimensional thoracic space while maintaining structural order. And the next image shows Hess-Murray's law. It summarizes diameter relationship in symmetric dichotomous airway branching. According to Hess-Murray law, cube of parent airway diameter is equal to sum of cubes of daughter diameters. This results in predictable diameter reduction of approximately 0.79 per generation, which governs airway size progression across generations.